Hello friends, welcome again. This is week 4 and this week is focused on gel 3D printing. Till now, in previous 3 weeks, we learned about the basics of 3D printing, we learned about different available protocols, and then we focused on the polymer based 3D printing in which fused filament fabrication or extrusion printing were explored. Now, in this particular week, we will be discussing mainly on the gel 3D printing. This is also known as the biogels or bio 3D printing. It has also numerous applications, and specifically, it is also considered as one of the advanced additive manufacturing or 3D printing technology. Here again, we are interested in making the complex component similar to our previous practice in the form of layer by layer structures, and this has gained the special attention of the researchers, specifically in the area of biomedical engineering. We are interested more to use this in tissue engineering, in soft robotics, and in food manufacturing. One of the common reasons for this type of applications are because of its flexibility, biocompatibility, bioactivity in nature of the gels that are commercially available. As you can see in this screen, this is one of the commercial printer, and right now this open source printer, the make is LAV, and you see here there are two extruder head. Extruder 1 is heating arrangement and extruder 2 is without heating arrangement, and we have a bed over here. So through the heating arrangement I can raise the temperature. Normally we work up to 60 or 70 degrees Celsius, and here is something like on off type switch. You can see a little video working of this machine that will be more better to you. Now this is actually the 3D printing going on. So through the extruder 1, you can see the component is being printed in the petri dish. So this is using a different type of gels. So at this moment the other extruder is ideal. So this is a syringe attached to the extruder, and we are printing a typical meta structure. So out of the needle some gel is coming, and the part is being fabricated in the petri dish. This is actually the product development using this open source 3D printer. So let us understand what are the key features. One of the best thing with this is the material flexibility. Whatever the gels we use, they can mimic actually the biological tissues and are easy to customize. Basically, what I need is whatever the component we manufacture, it must take the contour of the body. So then it will be easy to attach those component for any prosthetic or implantable application. Then precision and complexity, of course, this is capable of making any intricate shape. We have a lot of conformability requirement for the different biomedical applications, and these can be easily addressed, or this can be achieved by using this type of the 3D printing process. Then of course the biocompatibility and adaptability issues are very much within this domain. The applications are in biomedical, in bioprinting, in soft roboting, and food industry. And now this is the typical example to understand what type of gels we can use. One of the common example that I gave is like we can even use our toothpaste to print within the domain of this process. What the idea is, like suppose I squeeze on the paste, and there is a paste coming from the one end of the tube, right? So it has a expansion along the length, but along the width the expansion is controlled. So I need a gel type material which behaves like this. Like two examples I have put: one is the windshield glass sealant and another is the Anabond 666T plus. This is used in the fitting of the gaskets for the automobile engines. So what we have done is, like for the beginners, if you are just starting this first time, you can use these type of commercially available tubes, and can fill into your syringe, right, which is of course a consumable, not costing more than 5 to 6 rupees, and can try printing some of your initial component without spending much cost on the typical gels, just for the training purpose, right? So that is the only idea, to explain, like even the tubes that are used for the sealant in the windscreen of the car, or in the gasket, that can be used for printing, because these are really stable gels, in which along the width side I am not getting any expansion, but along the length side, of course, I can push the material through the extruder, and can print the component layer by layer. Specifically, if I talk about the hydrogels, they are basically hydrophilic polymers, and they form a 3D network capable of holding significant amount of water. The properties include, like, they are soft, they are biocompatible, they are tunable material. We have a lot of application in drug delivery and in bioprinting application. Some of the common example is like alginate, we use gelatin, we use polyethylene glycol, we use hyaluronic acid. One typical application just I want to highlight, like suppose you are interested in developing some bandage for a burnt injury case, and you want to develop some gel which can be useful for a, let us say, 50, 60, 80% burnt injury case. So what actually we do in our lab is, we use the fish skin based gel, which are available with the, of course, you must have a collaborator with some biotechnology department who can actually make a gel from the fish skin, and then we print that gel, and in the form of a bandage, or like some rectangular strips that can be put on the on some wound, or like specifically in the burnt injury case, because it gives a lot of soothing effect to the patient. So commercially alginate based gels, like which are having, developed from using some algae type material, like, or a gelatin based, are very commonly being used in market. Then we have a organogels. This contains a solvent, which is organic solvent. We can use a non-aqueous stable material. Of course, it is under various condition it must be stable, and one common thing is it is hydrophobic, whereas in the previous case it was non-hydrophobic, so it is hydrophilic in that case. So its application is in electronics, sensor, and soft robotics. One of the common example is the polyvinyl alcohol and fatty acid based gels that are being used. Then there is another category, that is of the composite gels. So these are secondary materials which have nanoparticles or the fibers. Uh, as these are secondary material, they have enhanced mechanical strength, better thermal stability and conductivity. They have application in load bearing scaffolds, conducting materials, smart devices. We can use it for a case in which I need to develop something for bearing a load in case of the scaffolds, right? Some of the examples are like hydrogel nanoparticle composites, for example, graphene oxide infused hydrogels, then cellulose or silk based reinforcement in the gel matrix. Then there are, of course, smart gels which are used for the 4D application. Like typically when I talk about 4D, these are the stimuli responsive gels. So these respond to the environment. There can be, like for the 4D, stimulus can be pH value, the stimulus can be temperature, the stimulant can be chemical energy, maybe the light, or more than one stimulus can be there. So they have a shape memory or programmable functionalities. People have reported 1D, two-way, three-way programming for these type of gels. So again, the application in 4D and soft robotics. A typical example is poly N isopropyl acrylamide. This is one type of gel that is very commonly used for 4D application. This has a stimulus as temperature. Then there are pH sensitive gels. Of course, the chitosan and PLA. Chitosan, we know that biocompatible, ceramic type material, and PLA, of course, the biocompatible polymer. we make a gel with these type of materials. They are of course the pH sensitive, and can we can make a lot of biosensors using these type of gels. Then there is another category which we call as the bioink gels. These are normally designed to encapsulate living cell during 3D printing. They have high biocompatibility, appropriate viscosity for cell survival. The typical application is in bioprinting of tissues and organs. Example is like collagen-based bioinks, fibrin gels for different type of tissues. Normally, these are made into the final component based upon UV cross-linking, and normally these type of bioink gels, the final part is of high dimensional accuracy, and they have the high precision also. Now coming to the preparation of these type of gels using thermoplastic. So material selection is important. So what we do is we select a thermoplastic polymer based upon the desired property, like for what melting range I am interested, mechanical strength, biodegradability, etc. So we have different examples of thermoplastic that we use for this type of application. This includes PCL, that is polycaprolactone, very commonly used biocompatible material, PLA, then TPU, again very common for making some foot sensors, then PVDF, of course polyvinyl difluoride, a piezoelectric based material, very commonly used for making these type of gels. Then the selection of solvent is also very important. Some of the examples are like using the acetone, dimethyl sulfoxide, DMSO, very commonly used, hydrochloric acid, chloroform, DMF. These type of solvents are very commonly used. Then the next step involves the mixing and dissolution. So what we have to do is we have to accurately measure the polymer in by weight. Normally we select, and solvent concentration and composition, it may vary 10 to 20%. Then we go for the dissolution stage, and then finally we go for the addition of the different type of additives, which may be the plasticizer like the glycerol, or there can be adding of cross linkers to modify the gel properties. Then the next stage involves the curing, so in which we go for the cooling step, we go for the cross linking. Again, cross linking is again categorized like thermal cross linking we are interested, or UV cross linking, and the degassing stage. So all these are the sub parts of the curing process. So after the curing is done, we go for the characterization and testing. So one of the basic thing is we go for the rheological analysis. So for that we go for the viscosity, so that we can understand what is the smooth flow for this type of developed gel through the nozzle. Then we go for the understanding of their shear thinning behavior. Then based upon these basic tests, we adjust the formulation if necessary, and then we load this gel into the extruder or printer, which has again some steps like preheat the gel required on case to case basis, load into the syringe or the cartridge of the 3D printer, and then we go for the testing the extrusion to ensure smooth and uniform flow. As regard to the operating processor for gel printer, so again the similar way we go for the STL file generation. There are many commercial open source software available through which we generate the G code, and there are some standard process like setting the printing speed, nozzle diameter, or some other hardware setting are there. So I will show you some of the interface, like once we go to the bioprint or gel print window, like you can see on your screen. So we got a signal to get login. Then the next stage is we have to go for the G code file. So we import it over here. So this is the interface. So here we still no pressure level or temperature level at 0 has been set. Then once you are done with the G code file, so you can name it, put a date, size, right? So clicking on the wrench over here, so we can sort the items maybe in ascending order, descending order, and the G code selection is complete. Then we connect the printer. So this will be the interface as it is showing. Then on the z axis we can control the up down movement. Then we have to home the extruder axis. So this will be the next interface that will be available on my screen. Then we go for the home the x and y axis. Then we select the base plate. So like I have shown in the picture, we use the petri dish, right? So we can have a different type of well plates. This is the loading of material into the syringe. So in this particular example, the Anabond 660 plus gel is being loaded into the syringe, right? So in this case, a needle is being attached, so we can have a different thickness of these type of syringe needles, right? And we tighten the knob. So go for the calibration. So for the calibration stage, we have plus minus button. We basically control the pressure as per the requirement, and then we adjust the pressure between 30 to 50 psi for this specific material like Anabond gel. Now this is of course a commercial gel, so for each type of gels I have to do for different trial and error to understand what should be the exact pressure value. So we press the extrude button to stop the flow, so that we understand that the flow is uniform. Then we have to go for the step size. We can select from 10 mm to 1 mm. So the software will help us in understanding the movement in the z axis. So we can control that. And once the z axis is in place for extruder 1 to run the pressure, then we deposit a small amount of material, and then we repeat this process again and again. So there is a one observation, like sometimes this syringe moves slightly when you hit the extrude, right? So there, when I just put it at the extrude button, so there is a very slight movement. So if it is low, then it will not create a good dot, right? So ultimately I need a good dot over here, so no material will come out. So if it is too high, then a dangling line will be created. So I have to basically adjust it by trial and error, right? So once you correct the position, so we have to update the left under extruder 1 and then calibrate the right portion. So this is the interface that will be available. So once my tool is calibrated, we have to go for the print, and then we can see the the fabricated part. So there are some of the parameters that I can optimize for my printer on my 3D gel printer. Like I can control the pressure, printing speed, layer height, gel viscosity. Like in one of the example, it has put, like they have put some pressure in 180, 200 to 20 psi, then printing speed in per second, layer height, and gel viscosity. And based upon this, they performed some DOE, and in this DOE, some Taguchi based analysis L9 has been used, and depending upon the ASTM D638 tensile coupon, ASTM D695 compressive coupon, and ASTM D790 for the flexural coupon has been developed. So you can see the final component is available with me, and I can go for the different type of the mechanical testing. Then the like typical statistical way of looking into the things, we can go for the optimization part, like whether I am interested in some property as a smaller the better or larger the better or nominal the best type case, like we go for the signal to noise ratio analysis, right? So that can be done using the Taguchi. Like after the ANOVA analysis of variance, we can find out the top peak values which are the best setting for operating these type of conditions. Like from the analysis of variance, it came to know that like this anti nozzle temperature and pressure, they come out to be the significant parameter for some specific mechanical property with a contribution of 72% and 21% for the better mechanical property using this type of setting. So there is a need to determine the optimal parameters. So S by N ratio calculation is one of the way. Then we can go for the validation by doing the confirmatory experiment a number of times, right? This is the overview of the gel printing. I believe that this information is useful. In my next lecture, I will explain one typical case study using a gel printing setup for the industrial application, and how we can control some of the parameters. I hope the information was useful. So keep watching. Thank you very much.